Yeah. So, the course title which we are going to deal with this semester is Organic Photochemistry and Pericyclic reactions. See, till mid semester we will be trying to concentrate on the first part, that is your organic photochemistry, and after mid semester we will be trying to discuss about the pericyclic reactions. Today class I will just try to introduce you to organic photochemistry. So, what organic photochemistry is basically, it is nothing but it tells you about the interaction of light with organic material. So, what happens in brief, when a light interacts with your ground state reactant R, it tries to undergo different types of transformation to give you the product P. The basic or the simplest representation of organic photochemistry can be written like this. You have an R which we call them as a ground state reactant, you shine with light H mu, which we call as a photon. This R now undergoes different sort of transformations to give you the product P. We call that as a ground state product. So, this is the simplest representation of an organic photochemistry. You guys know about organic chemical reactions. Same way you have an R, you put some reagent, then your R get transformed into your P. In organic photochemistry, your reagent is nothing but it is your H mu. Now, what we will try to do is now briefly understand how this R is getting transformed into P. That is a broad spectrum of looking into organic photochemistry. You take a ground state reactant, as I earlier mentioned, you shine light on it. What happens? You have a ground state reactant. Once the light shines on this reactant now transforms from its, if you consider a lower energy E0, from its ground state energy to an excited state energy, right. This most of the time these transitions are electronic transition. So, your R, once it interacts with the light, it becomes excited state reactant, which we will call as R star. Yeah. Consider. So, your R is not getting converted into your excited state reactant. The point is here to be noted is that your R star is not going to give you the product P. See, this R star will not give you the final ground state product P, or in other words it is not going to give you the isolated product. So, what this R star does now in the excited state? It does an electron transfer, or it can do an atom transfer, or it can break the bond, or it can make a bond to give you an intermediate I. Okay. The intermediate I can be a ground state species, but it is a very short lived species. So, that this intermediate gets transformed immediately to give you the product P. So, what we say that R star gives you a short lived intermediate. The short lived intermediate can be like carbene, or it can be a nitrene or diradicals. So, which can react very fast to give you the product P. See, this is a ground state product, or we can call them as an isolated product. You can isolate this guys. See, the point is that the I, that also is a ground state species, that also is a ground state product, but only the thing is that I is highly reactive, that it immediately gets transformed to your P. So, this is the broader outlook of your organic photochemistry. So, you if you just review back, you have a ground state reactant which interacts with your light, gets excited to its excited state, which you call as R star, and this excited state reactant then does an atom transfer or electron transfer, bond breaking or bond making to give you the short lived intermediate like carbene, nitrene or diradicals, and this short lived intermediate can give you the final product P. It is clear. Now, what we will do is that we will take each of these steps like R to R star and get into detail. Then we will try to understand how R star gets to I and finally I to P. So, we will start to understand this step first, that is R to R star. To understand this part, that is R to R star, we will take a simplest molecule in the ground state level, like well characterized and simplest molecule, for example formaldehyde. Okay. So, now we have a formaldehyde molecule. If I shine light on this formaldehyde molecule, what happens? Say, I am not going to give you any selection, I am just saying that you have a formaldehyde molecule, you are going to shine light on this. So, what are the plausible transitions? That means, all the transitions which this formaldehyde can do, just we will write that part alone. Okay. All the transitions, we are not going to ignore any transitions. So, you have a sigma, we will write the HOMO of that first, sigma CO, then you have a pi, then you have a non bonded electrons, right. So, you have a, this we will consider as the HOMO, then we will write a sigma star, the LUMO of this, right. Now, we will see that once the light comes, what are the transitions you are going to see. We will start from N. Okay. So, the first transition you can think about is N pi star. Next we can see N sigma star transition. So, from non bonded we can see this both the transition N pi star as well as N sigma star. So, I am doing all the transitions, all the plausible. right. Then we can have a, from pi we will have a pi pi star transition, and then we will have a pi sigma star transition. From sigma you can have a sigma pi star transition, then you have a sigma sigma star transition. So, if you take a formaldehyde and if you shine light, you can see 6 type of transitions. From non-bonded you can see 2 transitions, from your pi 2 and from your sigma 2 transition. That is good. Now, I am slowly going to put some criterias in this transition. I am going to say that, see guys, I am going to give you very minimum amount of energy. I am not going to tell the number, just for crude, very minimum amount of energy I am going to shine on this formaldehyde. So, what transition we can observe? The minimum energy, with that what transition we can, it can happen, your n pi star transition, right. Others transition needs more energy. So, with the minimum amount of energy I can do my n pi star transition. So, shall we take that, we can put that selection and take this n pi star transition out. Okay. So, putting a selection, I am going to do a possible transition for that particular selection, that is n pi star transition. So, something I am missing in this transition while writing this electrons, what I am missing on? Anything from you? While writing this electron I am missing something, spin, very good. So, shall we introduce now the spin into this? See, first I am introducing a small concept called selection of small energy. I am just picking out my n pi star transition. Now, I am introducing one more concept called spin, right. So, I can write spin in 2 ways. One, it can be in this direction, your spin, or it can be in this direction, right. One can be parallel, another can be anti-parallel. So, we call this parallel spin as triplet and we call this anti-parallel spin as singlet. It is not because of that exactly why we call them as singlet and triplet. Why we call this as a triplet? For example, you take this triplet state, consider this triplet state. For one spin we can write plus of, okay, I am taking the triplet. For another state I am writing plus of. So, in the presence of a magnetic field, what happens? This 2 spin can combine to give you a new spin which can be 1, right, a new spin will be formed. Now, what happens, this spin can align 3 ways with the magnetic field. One, it can align with the direction of the magnetic field, which you call as plus 1, or it can align opposite to your magnetic field, which you call as minus 1, or it will be a right angle to your magnetic field, call as 0. So, now you have 3 states, okay. That is why we call them as a triplet. Clear? Why we call them as a singlet triplet? Yeah, for general view we say that if it is a parallel spin, then you say it is like triplet, and if it is an anti-parallel spin you say it is a singlet, but actually speaking it is like this. Okay. How to represent now a n pi star singlet state? So, the best way of writing this is singlet n pi star. This you write as triplet n pi star. That is how we represent singlet if it is a singlet pi pi star, then you write singlet pi pi star transition and triplet pi pi star transition. It's clear, up to this it's clear. So, we have now introduced a concept of spin into this, and we are saying that singlet and triplet. Now, what I am going to do, I am going to introduce one more concept here, is energy. First I have introduced a concept of spin, now I am going to introduce a concept of energy. So, if I introduce a concept of energy, okay, I say this is S0, which has a ground state energy. Then I will write my S1, which is your excited state energy. You can now place your triplet as T. You can place either above singlet based on their energy level, or you can place equal to your singlet, or you can place below the singlet, right. So, I am going to place that below the singlet, fine. So, now we will see why I am placing this triplet below my singlet. That means, the energy of triplet is lesser than singlet. Why I am doing so? Any idea? Why I place my triplet below my singlet? Anyone? Okay. It is nothing but what you studied in your Unz rule. What your Unz rule says that? See, if you have a singlet, this always try to come together, right. You have two orbitals with an antiparallel, they always try to come together, and once they come together they repel away. They come together and they repel, they do not like to be together because they repel. But if you draw triplet, this chance is not possible at all, because they never like to come together, they stay cleanly away from them, and they are saying that there is no repulsion, I am happy. So, I will be always the lower energy. See, in singlet you have a sort of maximum repulsion, they have an habit to coming together and repelling away from each other. That is why your singlet has much higher energy compared to your triplet. So, that is why I put my S0 here, S1 and T1, clear. Now, we will take formaldehyde, okay, and see that n pi star transition. We all try to put all the information what we understood now. Okay. So, if I take my formaldehyde molecule and pass like shine like with minimum energy, so I can write my S0, my S1, write my T1, this is n pi star transition, right. You can write on the top, that is also not a big problem, it is an n pi star transition. So, you have an S0 to S1. So, your once the light shines, you have your non bonded electron going to a pi star, n pi star transition takes place. Now, what this molecule does in S1? Just generally speaking, what it can do when it is in S1? It can come down, okay. It can come down in two ways. One, it can come down giving out the light, okay, or it can come down by giving out you the heat, right. This two way it can try to do. Once it comes down by giving out light, okay, you call that as a fluorescent process, which we know. Okay. We will get into that little bit later. Or other thing what it can do, yeah, it can come down to its S0 state, or what it can do, it can do a non-radiative process. This is how it can come to S0. If it does not like to do, it does not want to come to S0, what it can do? It can go to T1. That process it can go by giving out the light, right. From T1 then it can come back to S0, same way it can give the light out, or it can do a right. So, it can do this sort of when it goes from R to R star, it has have an option of doing this. Later on we will see why when it has to do to photophysical, that is S0, or when it has to undergo an intersystem crossing to give triplet. We will try to understand that conditions later on. Okay, now just we will try to understand the process. Then we have a lot of things which we have to say why it has to go to S0 or which part it tries to take. We will now slowly label this each process. If it goes from S1 to S0 giving out light, you call this as fluorescence, right. If it goes from S1 to S0 by giving out heat, you call this as internal conversion, which you call as IC. If it goes from S1 to T1 giving out light, this you call as intersystem crossing. Then if you have T1 to S0 plus, you call this as, very good. Again you can call this as internal conversion. So, it can do this type of all the thing, that is clear. Now, what we will try to see, if you try to understand this process, okay, for example, with respect to number, you will be knowing much better. For example, if I ask like which process will be faster, whether it is fluorescent or it will be a phosphorescence, yeah, phosphorescence, because it has to flip its spin, because it is coming from a triplet to singlet. So, knowing that with respect to number will tell you more. So, we will see the same process with respect to number, we will put the numbers on the transition, so that we get an idea about it. See, for fluorescence, or we can write it in a separate page so that you can, because it does not work for formaldehyde, it works for general ketones, this numbers. If I take an, for example, R for a general ketone S0, then I have an S1, I have my G1, talking of N pi star. So, we like take for a ketone and try to understand how this thing. See, for fluorescent, okay, the rate constant for fluorescent Kf, that will be 10 to the power of 5 to 10 to the power of 6 second inverse. See how fast the process is. It goes S0 to S1, but from S1 to S0 it does not need any spin flipping, right. So, it comes down so fast. So, it takes only 10 to the power 5 to 10 to the power 6 second inverse, clear. Now, we will just compare that with phosphorescence and see how much time it takes. If you take for Kp, that this process, the rate constant for phosphorescence, where it has to flip its spin, right. It has to come from triplet to ground state singlet. Any idea how much, whether it will be a fast process or slow process? It should be a slow process. This numbers, because we have this vague number 10 to the power of 5, we cannot remember how slow it can be. Yes, very good. So, it will be from 10 to the power of 2 to 10 to the power of 3 second inverse. See how much it gets delayed. Yeah, it gets delayed so much, right. Then we can see this process, which is your internal conversion, how fast it can be. It can be faster than your fluorescence or slower than your fluorescence, internal conversion, where it just radiates the heat, that is all. It should be faster or slower? Slower, just it has to radiate the heat, that is all it has to do. Slower, are you sure? It does like 10 to the power of 14 second inverse. So, your IC is 10 to the power of 14 second inverse, does that job so fast. See, that is why I said that this number has lot of meaning. It is not like knowing the process. It said that yes, going from S1 to S0, yes, it is fluorescence, going from T1 to S0 it is phosphorescence, that is fine, but understanding with respect to numbers tells you how, which process is faster, which is a very delayed process, all these things. Then we will just get in detail and try to understand why this process are slow and faster, okay, slowly. First we will see the numbers. Any idea about this ISE, what number this can be, this inter-system crossing? It is again a spin flipping process, right, but normally you know how this goes. S1 to T1 it will not jump like that. How it does, you have any idea? Times, it will be slower than IC, whether it will be slower than your phosphorescence. No, whether the process ISE will be slower than phosphorescence or it will be faster than phosphorescence, because both are spin flipping process. It should be faster. So, it does like 10 to the power of 8 to 10 to the power of 12 second inverse. That is why, because the energy gap between your singlet and triplet is sometimes are very small, not compared to your T1 to S0. T1 to S0 the energy gap is huge, but S1 to T1 the energy gap most of the time will be small. That is why the process, even it does a spin flipping, it does fast. So, you get a rough idea now, right, how this whole process having the numbers, that is good. Any doubt on this? Now, we will same transition, I will ask you like S0, you write S0, right, and you say that you write only, most of the time you try to write only S1. See, there are other levels also there, right, S2 there can be, S3 can write up to Sn, have all these transitions, all the energy levels available there, but all the time we try to push from S0 to S1 and then we talk all the chemistry or physics, photophysics or photochemistry. We never worry about S2 or S3. See, if you have a transition, I can say it can go to S0 to S1, or it can go to S2, it can go to S3, or it can keep on going. So, that is all is allowed, right. So, it happens only from S1. Any idea why? What is that famous rule?
Slower than the electron transition.
Yeah. What we can say is that vibrational relaxation is so fast, okay, this all states collides immediately and collapse into S1 state. Okay. The vibrational relaxation is so fast, they just collapse and they all fall into the S1 state. That is why we most of the time we do not consider S2, S3, S4, but there are some molecules where you can see from S2, S3, S4 states. What are they? Some molecules which can do photophysics from S2, S3, azulines. If you have azulene type of molecule, then it all happens from S2, S3 also. But most of the general molecules which we are going to consider, most of the time the transition tries to happen from S1. So, that rule is called as Kasha's rule. You call this as a Kasha's rule. What it says that your fluorescent will be completely independent, okay, of the excited state. That means, your fluorescent occurs only from the S1 state. It is completely independent of your excited state. It will all the time it will try to occur from your S1 state only. That is called your famous Kasha's rule. Because your S3, S2 all if you see, the process will be very fast, it will be greater than your 10 to the power of 14. So, you cannot even see them, they all will vibrationally they collapse and they get to S1. That is why your all the fluorescence we try to talk from only the S1 state. Clear? Okay, this we call as Kasha's rule.
Please repeat what is the rule.
Your fluorescence is independent of your excited state. It occurs most of the time from your first singlet excited state. Okay. Now, what we will try, so we were trying to understand this process R to R star. That is what we took the first step, we said we will try to understand this first step in detail. So, how we started, we took a simplest photochemistry scheme, then we slowly moved down, we said it is an R which gives you P interacting with H mu, that is your simplest photochemistry representation. Then we went little bit down and made a broader outlook. We said that R gets excited to your R star, then gives you a short lived intermediate I, which then gives you a product P. After that, what we said, we will take each step and try to understand in detail. So, we took R to R star initially, then we said that it can undergo a transition, all the possible transition. Then I brought us some sort of criteria and said that I will give you a minimum energy. Then we took the smallest transition n pi star. When we did n pi star, we included the concept of spin, we introduced singlet and triplet. Then slowly we introduced the energy concept and we said that singlet as well as triplet comes down and singlet will be in the higher energy generally. Okay, there are some cases where it is reverse also. And then we summarized everything by using a type of Jablonski diagram. and we studied Kasha's rule. So, from R to R star, can I write like this now? I get my R, I get my R star, which will be my singlet, right. So, S1, and then it undergoes a intersystem crossing to give me my R star triplet, okay, and this will give me the I, and which give you the P. See, so I have just now expanded that schematic representation. See, we have to take this part now. In the next class, what we will do, we will try to understand in detail how this R star to S to R star to T happens, like just by orbital structure. We will see how this transition occurs. It is just a few minutes we will discuss on that. Once we discuss, then we will move from R star to I. We will try to understand how R star gets transformed into I, and finally we will try to understand how I moves to P. Once we next 2 hour class, we will finish the introduction part. So, this will be the introduction of organic photochemistry. Then we will slowly get into our reactions. It is clear? So, what happens is that normally if you do a chemical reaction, if you take a reagent, what do? You do in 1 mole. You always say that it is 1 mole of reactant and 1 mole of reagent I am adding in to get my product. Same like that, we also can communicate for photon also. We say 1 mole of photon equal to, we can call them as Einstein, that is 6 into 10 to the power of 23 photons. This we call as 1 mole of photon. Why we should know this? Because this will tell us the energy which we need to carry out our photochemical reaction. For example, if I take 1 mole of photon of 200 nanometer. So, I am taking a light whose wavelength is 200 nanometer. So, I am taking 1 mole of photon of 200 nanometer. So, how much of energy this is going to give you? You can easily calculate, because you know the formula E is equal to h mu. With that you can calculate, and it comes normally 150 kilocalories per mole. If I want to carry out some reactions which needs an energy to break a bond of 150 kilocalories per mole, then I will think of doing my chemistry in 200 nanometer. That is 1 mole of photon of 200 nanometer will give me 150 kilocalories per mole. That much of energy I will get. That is good. So, same way, if I use 1 mole of photon of 300 nanometer, just think, if I am going to use a wavelength of light of 300 nanometer, then how much energy I should get. And you know that as the wavelength increases, what happens to your energy? In other hand, it will decrease. So, 1 mole of photon of 300 nanometer will subsequently will give me 100 kilocalories per mole. It is a good number to remember. So, you have a 300 nanometer, you have 150 kilocalories. If I decrease by 300, that is 100 nanometer down, I am decreasing my energy by 50 kilocalories, which is nice. Now, same way, if I go to 500 nanometer, for example, I see that how much is 1 mole of photon of 500 nanometer corresponds. Then you can say it is 60 kilocalories per mole. See, most of your organic chemistry reactions happens up to this region like 500 nanometer. Most of your organic chemical reactions, most of your transitions, electronic transition like n pi star, pi star, all these transitions will come around 500 nanometer where you can do the chemistry, because if you see the energy, it is only about 60 kilocalories per mole. If I go down, that is like still down of 700 nanometer, then you can see the energy gets subsequently very low and becomes like 43 kilocalories per mole. You can just do some excitation here, that is all. Okay, you do not see big chemistry happening like bond breaking, bond making like that. See, I am talking about general things. Okay, there are exceptional cases, but I am talking generally what happens. This 43 kilocalories per mole, we call this as red light. That is good. If you want to still further move down and see like how much nanometer, like if I, for example, if I take 10,000 nanometer, what will happen in this? You don't get your possible electronic transition which you are talking about. So, what you are going to expect in this region? You are going to just expect vibrational and rotational excitations. These are going to happen in this region. So, at 10,000 nanometer you can expect vibrational and rotational excitations. This you can see around at 10,000 nanometer. If I still go, that is at 10 to the power of 8 nanometer, what you are going to expect? Here you are going to, here what happens? You will have an electron spin type of excitation. Your electron spins gets excited, but this can be done only in presence of magnetic field. So, you get electrons spin excited, but this should be done in presence of, it happens in presence of magnetic field. Okay. If I go, if I take 1 mole of photon of 10 to the power of 11 nanometer, what we are going to see around in this region? You will be seeing your nuclear spin excitation, where your all your NMR you try to do, right. So, that you are going to see in this region, nuclear spin excitation. This also should be done in presence of, this happens in presence of magnetic field. So, in photochemistry what we are going to try to do, we are going to concentrate mostly up to your 500 nanometers. So, you see all your most of your organic photochemistry happening in this region, except few in 60 calories, but most of your chemistry happens from 200 to 400, 450 nanometers. So, how to, now the next question comes to in your mind is that how we can going to make this 200 nanometer, because you have a light, how we are going to get 200 nanometer light, how we are going to get 300 nanometer light and 500 nanometer lights. See, there are specific one, if you have a lamp which gives you a radiation of lights. So, you can use a specific filter most of the time. If you can use a specific filter, you can get across. For example, if I use quartz type of filters, then I get a light greater than your 200 nanometers. If I am going to try to use Pyrex, then it is cut off from 290 to 310 nanometer, you get light above that. For example, if I use copper sulphate solution 350 and sodium nitrate solution like 410 nanometer, that is how you can make the selective in your reagent. That is how your photo reagent becomes very selective. For example, I want to do some chemical, some photochemical reactions in the visible light, that is a wavelength of greater 410 nanometer. Then what I do, I take the apparatus, I use a filter. The filter can be 1 molar sodium nitrate solution. then I get a light around 410 nanometer. So, I can selectively excite the bond or selectively do some photochemical reaction where it needs 410 nanometer. For example, I have a big molecule and I want to excite only the particular functional group, which can be excited at 350 nanometer. I do not want to touch other things. Then you have like specific lights which you can use. For example, I want to do a chemistry greater than 350 nanometer. I do not want to affect any other compounds which are playing around 250, which can excite at 250. I want to do chemistry only greater than 350 nanometer. Then you can use a copper sulfate solution, which will give you light after 350 nanometer. Like that you can do some selection of your reagents. So, that is why this photons, understanding about your reagent in R to R star transition plays a important role. Once you know this R to R star transition, one more thing you have to understand in this step, that is we call as photochemical inefficiency steps. So, we can call them as photochemical inefficiency step when you compare to that of So, what I said initially, you have an R and this R, as we said, gets excited to your R star. Okay. We can say now then your R star gets to your I, this I gives you the product P, but not true in all the case that your R star should give you the intermediate I. Sometime what happens, your R star can undergo a process to give you the starting material R back. Like for example, your fluorescent process where your R gets excited to your R star, it does not want to undergo an intersystem crossing and then give you an intermediate. Instead of that, this R star can come back to your R itself. So, it gets excited and gets back to your starting material itself. So, that you can have. In same way, there are cases where your I can also get back to your R. So, this process where for example, I am giving a photon, it is not been completely used to convert your R to P. What happens, this photons, some of this energy has been used and then it gives me back my starting material. In some case, this intermediate can also give me the R back. So, basically we call these steps are inefficiency step. These are very important when you do your quantum field calculations. That part we will see in detail how to do a quantum field calculation. There this type of things can occur. Same way we can tries to understand one more aspect of photochemical, that is product inefficiency can also take place. That means, if I am doing a reaction, the R does not need to give me only one product P. So, what happens, you have your R, this R takes your H mu, it can get excited to R star. As I mentioned earlier, this R star can give me my R back, or this R star can give me back my this R star can give you the I and then gives you P, that is fine. But this R star can not only give me one intermediate, they can give me another intermediate which we call as I prime, and this can give me another product which we call as P prime. Same way, your I can also give me another product which is I double prime we can call, and this can give me also another product can get P double prime. So, you see many things can happens. First case we have said that R goes to R star and gives me back my R. The second case we have said, see, your R gets excited to R star, gives me another intermediate I prime, which gives me different product, or my R star gives to I and gives me I double prime, giving me different products. So, I am getting like 3 products. So, this 2 steps which we call as, this is photochemically, previously what we discussed, this is we call some inefficiency steps, and this will call as a product inefficiency step. This 2 you should understand before we have to do quantum Hill calculations, right. So, this is how I am going to end up this, saying that, see, if you have an R, R gets excited to your R star singlet, and R star singlet can give me R star triplet. So, we will end up today with this note. From next class we will start to understand the second step, that is how R singlet is converted, undergoes inter-system crossing to give R triplet, and then R triplet giving you the I, and from I we can see how we can get the product P. So, from this class we will do that.